Hello, my name is Katharine Adamyk, and I'm seeking a position starting in fall 2022. I finished my PhD in 2020 with Agnes Beaudry at the University of Colorado, and I'm currently a postdoc at the University of Western Ontario working with Rick Jardine. My current work can be divided up into three main projects: problems in the Steenrod Algebra, some work in topological data analysis, and work with equivariant Hochschild constructions. My interests in general lie in heavily algebraic problems related to homotopy theory, often with an emphasis on computation. There's plenty I won't have time to talk about now, but would love to talk about in the networking session or via email, including ideas for undergraduate or early graduate student research. Here, I'll mostly focus on my newest project, which is in topological data analysis. One common construction in topological data analysis, or TDA, is the Vietoris-Rips simplicial complex. So given a data set, which here will be a finite set of points in a metric space, a one simplex is added between each pair of points that are within distance s of each other. Whenever all faces of a higher dimensional simplex are present, that simplex is included in the complex as well. As the distance parameter s increases, we get complexes with more and more simplices. These complexes have a density-based filtration called the Lesnik or degree-Rips complexes. A point in the dataset X is only included as a zero simplex of the Lesnik complex LSK of X if there are at least k other points within distance s of that point in X. For each pair of parameters s and k, taking the path components of LSKX gives a clustering of the dataset. Taken together, these clusterings form what is called a multi-parameter hierarchical clustering. Jardine introduced the notion of layer points within this context of Lesnik complexes. In my preprint Stability for Layer Points, I give a more general treatment of layer points and then return to a focus on Lesnik complexes to prove specific stability results for subsampling. So given a hierarchical clustering H, indexed by Rn with a possibly interesting ordering, there's a partially ordered set, gamma of H, whose elements are SA, where A is a cluster in our hierarchical clustering at the set of parameters S. An element TB is less than or equal to SA if T is less than or equal to S and B is contained in A. So roughly this means that the cluster B merges into the cluster A at some point. The layers of gamma H are equivalence classes of points corresponding to the same cluster. And layer points are points in each layer that mark a first occurrence of a cluster in some sense. More precisely, a point SA in our partially ordered set gamma H is going to be a global layer point if for all TB strictly less than SA, B is not equal to A. Or possibly there are no TB less than SA. In this paper, I give a description of the possible forms of layers. What types of equivalence classes can we see appear here? For multi-parameter hierarchical clusterings, we can also get slice clusterings by allowing just one parameter to vary and holding the rest of the parameters constant. If a point in gamma H is a layer point for one of these slice clusterings, where the ith parameter is allowed to vary, we call it an ith parameter layer point. I show that a point is a global layer point if and only if it's an ith parameter layer point for all I. The ith parameter layer points can also be used to define a map from gamma H to lambda H, the set of all global layer points. As a consequence, any interleaving of hierarchical clusterings, which consists of maps F and G between the two clusterings satisfying certain conditions, induces a homotopy commutative diagram in layer points that looks like this. This is the first stability result. Essentially, it says that if two clusterings are similar, they give a similar poset of layer points. We would like such a diagram to exist interleaving the layer points for subsampling. So if we take a good sample from our data set, we want layer points for the clustering built from the subsample to be similar to the layer points we would get by clustering the whole data set. I show that this is true specifically for the slice clusterings of Lesnik complexes. So for any x, a sample of Y. We define LKY to be the slice clustering defined by the path components of LSKY, so holding K constant, and then L0X is the slice clustering of the path components of LS0X. And then we're also going to want to use L0XC, which is a truncated version of L0X. So I won't get into the details, but essentially it just cuts out a little bit of noise at the beginning of the clustering. I give bounds on distances between X and Y that ensure the layer points of LKY and L0XC are interleaved, as well as bounds that give the stronger result of a retract in layer points from LKY to L0XC. One drawback of this formulation of stability is that the distances between X and Y that I use are extremely sensitive to small changes, like adding a single point to the set Y. Moving forward, I hope to address this by either considering a measure theory approach or constructing a subpose set of the layer points that only includes layer points where a cluster changes by a certain number or percentage of points. Further in the future, I plan to focus on stability theorems in the multi-parameter case and persistent homotopy theory more generally. Next, I'll tell you a little bit about my work in the Steenrod Algebra. So in my preprint classifying and extending Q0 local A1 modules, which includes but also extends my dissertation work, I give a complete classification of modules over A1, which is a subalgebra of the Steenrod algebra, that have trivial homology with respect to the action of the element Q1. I then use an H0 localized Davis-Moholt spectral sequence to locate periodic families of elements in X groups over A1. This has applications to a lifting problem, one that determines whether a given A1 module can be given a compatible A module structure, where A is the whole Steenrod algebra. Any non-zero differentials in the spectral sequence correspond to obstructions to lifting. The differentials can all be computed in theory using the classification theorem in this paper, but in practice this involves the computationally intensive task of finding a particular decomposition of a very large tensor product. However, in this paper I give an explicit formula for the first non-zero differential, which sidesteps that decomposition problem. In ongoing work, I aim to do the same for the higher differentials as well. I also plan to continue work in the direction of classifying A1 modules by describing possible extensions between modules with trivial Q0 homology and modules with trivial Q1 homology. Further in the future, I am looking towards the classification of AN modules in general and related lifting problems. The last project I'll briefly summarize for you is my work on equivariant Hochschild invariants, and all of this work is joint with Tina Gerhardt, Katharine Hess, Inbar Klang, and Hannah Jiakong. In our papers, Computational Tools for Twisted Topological Hochschild Homology of Equivariant Spectra, and the upcoming Equivariant Hochschild Homologies from a Shadow Perspective, we consider equivariant analogs of Hochschild homology and topological Hochschild homology. In our first paper, we focus on developing computational tools for these constructions, including an equivariant Bochstedt spectral sequence. In our upcoming work, we show that these equivariant Hochschild constructions are all examples of shadow functors on some bicategory, a concept introduced by Ponto. This gives us some nice properties, such as Morita invariance as an immediate consequence, and we show that related constructions such as linearization maps can be framed in the context of shadows as well. Thank you very much for your time. You can find more about my research, my teaching, and the rest of my CV on my website, and I'm also available by email to answer any questions you might have. Thanks again.